Lecture 7.2, The Expanding Universe. As a reminder, in the last lecture, we saw that the Hubble law shows a relationship between the distance to a galaxy and its radial velocity away from us. The constant of proportionality h naught is called the Hubble constant. In this lecture, we'll talk a little bit more about what that observation means. So basically, it means that the universe is expanding. So the more distant a galaxy is away from us, the faster it's moving away from us. And so no matter what direction we look in space, we see all galaxies are moving away from us. And the farther away we look, the faster they're moving away from us. So it appears as though we seem to be in a special location in the universe, that everything seems to be moving away from us. So are we special? The answer is no. At least not in terms of expansion of the universe. So let's think about a simpler case where we have expansion just along a single dimension, say along the x-axis, along the number line. Here we are at position B, and the number line represents space, and the arrows represent the velocity of galaxies away from us at different locations. So the point is that if we switched our location from B over here to C, and then looked at the velocities of galaxies relative to us, we would see exactly the same thing. So here we think we're stationary, and say galaxy C is moving relative to us to the right. If we were on galaxy C and we looked back at B, now we would see galaxy B moving away from us to the left. Similarly, if we look at 2 units over, galaxy A would be appearing to move with 2 units of velocity away from us. Whereas before we saw that galaxy A was only moving 1 unit. So anyway, the point is that from the perspective of any point on the number line, everyone is going to see this uniform expansion away from them. So we're not at a special location in the universe. Everyone sees exactly the same thing. So another question that folks might have is, well, if the universe is expanding, what is it expanding into? Well, the answer to that might be itself. So if you think about the number line again, so if this is our universe right now, it extends from minus infinity to plus infinity, and yet, even though it's infinite in size, we can still imagine it to be stretching and expanding. So in the future, these little tick marks, which are marking, space itself, they're getting farther apart. So we're kind of pulling the number line apart. And so, well, what is it expanding into? It's just getting bigger. So the entire number line is stretching, but it's not like it's expanding into a void that wasn't expanding before. It's just that the entire number line is just in uniform expansion. So it's not really expanding into anything. You could just think of it expanding into itself if you want to. Here's another question. It turns out that from the expansion of the universe, you can get an age of the universe. So we're going to imagine that we're at position B. If you look at all the galaxies are moving away from us, imagine running time backwards. And so if you reverse the direction of time, instead of the galaxies all moving away from us, they're going to be all moving towards us. And now if you kind of run time backwards, then, initially, this is the motion of the galaxies all coming towards us. As you kind of go farther back into time, space will be shrinking more and more. And it turns out all of the galaxies, every point on the number line, all meets back at our position at exactly the same time. So it appears that there was a particular special moment in time where the expansion started. And so, if you go back a certain number of time steps back into the past, it would appear that the entire number line collapses on top of us. Again, everyone would think the same thing. Everyone sees the universe collapsing on them. And so this moment in time where the number line has been completely compressed into a point, that is the moment of the Big Bang. We can get an estimate of when that happened from a very simple calculation. We define the Hubble time, T sub h, as the time since the Big Bang, assuming the expansion rate is constant. So for a constant velocity expansion, the distance is just velocity times time. If we substitute the Hubble law, that actually should say V equals h naught times d, and solve for the Hubble time, you can see that the Hubble time is just 1 over the Hubble constant. So if we plug in 70 kilometers per second per megaparsecond and work out the units, so we've got, kilometers here and then megaparsecs there, so these units should actually cancel out, and so the units of h naught really is just a 1 over time. So we'd have to do a unit conversion to get megaparsecs into kilometers so that they cancel out. When you do that, it turns out that the Hubble time for a Hubble constant of 70 kilometers per megaparsec turns out to be about 14 billion years. So it appears that based on the motion of the galaxies, at least in this very crude approximation, that the expansion of the universe is constant, it appears that some event happened about 14 billion years ago to set the universe in motion. Another question one might ask is, where did the Big Bang happen? And you might already guess that there is no special location in the universe, that everyone sees exactly the same thing. So probably at every single point in space was involved in this initial expansion that set the universe in motion. So it wasn't that there was it's not like a firecracker going off and you can point and say, oh, the firecracker explosion happened over there. It's that every single point in space is equally involved in that initial expansion. Okay, I want to define a quantity that's going to be very helpful in the analysis that we're going to do for looking at models of the expansion of the universe. So this is called the scale factor. So imagine that, like right now, there's two galaxies, A and B, and they're kind of two tick marks apart from each other. If you look into the future as the universe expands, the galaxies and space itself will be stretching out. So notice that the distance between A and B is now larger, and that also the tick marks in space itself are also getting farther apart. So this is a key idea, is that when we look at the Hubble law, it's not that the galaxies are moving through space away from us. It's that the galaxies are relatively constant or relatively still at rest within space, and that they're just being carried along by the expansion of space itself. And that's supposed to be represented by the tick marks on these number lines. Okay, so we're going to define a few quantities here. The first is called the coordinate distance. The coordinate distance is what we measure. So it's given by the letter r, and it would be the distance between the two galaxies. So, so on this first number line, we see the distance between galaxies A and B. They're 2 units apart. Now, later, as the galaxies get carried apart from each other by the expansion of space, we see that the distance between these two galaxies is getting larger relative to our coordinate system. And so you could draw a little line from galaxy A, and it would fall on that tick mark. Kind of B would fall up on that tick mark. So the distance between A and B using our ruler would be 1, 2, 3, 4. So the coordinate distance between the two galaxies at a later time would be 4, whereas right now they're only 2 units apart. So again, that's what we would measure if we were to do some kind of astronomical observation. We would measure this distance within our own coordinate system. Okay, eta is called the co-moving distance. And that is the distance between two galaxies measured with a ruler that expands with space. So if you have two galaxies A and B, and we're going to assume that they're not moving through space, but rather they're at rest relative to space, they're just going to be carried along by the expansion of space. So notice that A and B are still 2 tick marks apart in the ruler that's kind of expanding with space. So this co-moving distance eta is still going to be 2 for the two galaxies. It was 2 right now, and it's going to be 2 forever, assuming again that they're not moving very fast relative to space. So in all the analysis that we're doing, we're going to assume that this co-moving distance between a pair of galaxies is always just going to be constant. So by definition, the co-moving distance is always equal to the coordinate distance at the present epoch. So if we write that the present epoch is t0, then the coordinate distance r sub t0 is always just going to be equal to eta, the co-moving distance. So r sub t0 is always equal to eta. In the future or in the past, eta and r at a different time might be different, but at the current epoch they're always the same. Okay, so the scale factor now can be defined. The scale factor is the constant of proportionality between the coordinate distance r and the co-moving distance eta. So we can write that r is equal to a times eta. So here's how this works. The scale factor is basically just telling us how much the tick marks of space have stretched compared to the present epoch. So here they've stretched by a factor of 2 relative to the current epoch. So the scale factor of the universe would be 2 here compared to what it is now. You can also verify that our coordinate distance of 4 between the two galaxies in the future is equal to the scale factor 2 times the co-moving distance 2. So 4 is equal to 2 times 2. The trivial case here is that at the present epoch, the coordinate distance 2 is just equal to the scale factor of 1 times the co-moving distance. By definition, the scale factor at the present epoch is always equal to 1. So a sub t naught is always equal to 1. Okay, so Another topic to kind of talk about generally before we start talking about models specifically has to do with cosmological redshift. We are imagining that a galaxy is uh, emitting a photon, some light. It's got a wavelength of lambda emit. As the universe stretches, so we're imagining that the universe is stretching while the photon is traveling from the galaxy to us. When we receive the photon, when we observe it, it's going to have a wavelength lambda observed. So the redshift of a galaxy, we talked about this before, it's just the difference between the observed and the emitted wavelengths divided by the emitted wavelength. The photon expands with the universe. So as space itself is stretching, the photon will stretch out with it. As the photon stretches out, increases its wavelength, it will reduce its energy and change the frequency and the wavelength. So because the wavelength stretches with the stretching of space, the wavelength is proportional to the scale factor. So since it's proportional, we can just write the redshift z in terms of the scale factors of the universe when the photon was emitted and observed. So we can solve for the scale factor when it was emitted. Remember that the scale factor of the universe at the present epoch, that's when we observe the photon. So A observed is 1 by definition. So that's 1. We solve for A emitted, and we get this very simple relationship that the scale factor of the universe when the galaxy is radiating its light, the scale factor of the universe at that point is equal to 1 over 1 plus the redshift. So if we can measure the redshift of light coming from a galaxy, we can directly and immediately tell how big the universe was at that time. So here's a very recent image from the Webb telescope. The Webb has been discovering galaxies farther than previously found. So here's an image showing a view from one of the Webb's cameras in the infrared, and within this image, that's a star. There's a few stars in here. There's a star, but a lot of the things that we see in this image are all galaxies. The Webb has a very sensitive spectrometer, and so it can take spectra of a lot of these objects. So, for example, the tiny little galaxy that's in that little box has been blown up, so it's right here. And then the spectra of that galaxy is right here. So these red lines are the H beta and H alpha lines. And I don't know if you can read it, but the scale here is it's in microns. So that's 2 microns, 3 microns, 4 microns. The H beta line is at 480 nanometers. So right here, this is almost at 2 microns. So that means that when the galaxy emitted these photons, it was at 480 nanometers, but now we're observing them at 1800 nanometers. So the redshift, you just take the difference of these two and divide it by the emitted value. So 1800 minus 480 divided by 480 turns out to be 2.75. That's the redshift of this galaxy. And then we can use this result that was on the previous slide to figure out how big the universe was when this galaxy emitted its light. And so it turns out 0.27. So in other words, the universe was about a third the size as it currently is when when this galaxy emitted its light. And you can see on here that folks have determined that this galaxy is about 11.3 billion light years away. We'll talk about how to calculate that a little bit later. As you go down the page, these four galaxies are at progressively farther and farther distances. So the one at the bottom, we can see that we're detecting that H beta line at a wavelength of 440 nanometers. So that has a redshift of 8.2, very high redshift galaxy. And when we calculate this, we find that the scale factor of the universe when this photon was emitted was 0.11. So roughly about 1/9 the size. So in other words, the universe has expanded by a factor of 9. It's 9 times larger now than it was when this galaxy emitted the light that we're just now detecting. And so the folks at the Webb telescope determined that this galaxy is about 13 billion light years away. One of the more distant objects that have been ever found. Okay, so in the next lecture, we will talk about a specific model about how the universe expands, and that'll let us calculate the look-back times that we were just talking about. Okay, that's the next lecture.